do you see the presentation?
Yes, we see, but second slide.
Sorry.
Oh.
Dear organizers and participants of conference, report utilization of GIS and augmented reality for the mining and role planning in dangerous spaces are presented for your attention. Report includes 3 parts: introduction, the presented motivation, state of art, the aim and objective of research, main results with methodology of pathfinding and AI application in the mining, approach of software realization, research and the approach of pathfinding in the mining system, and conclusions. At the moment, with the increase in the number of armed conflicts in the world, especially the Russian aggression in Ukraine, the problem of mine and different exo clearance become more and more urgent with every passing year. Ukraine is currently the most explosive containment country in the world. Due to mine contamination, the population is unable to carry out normal activities in the region, such as farming, foraging, and other activities. DSNS units are engaged in mine clearance, but the number of territories contained with explosive objects are enormous. A third of the territory of Ukraine, which was under occupation, is contained with mines and needs to be truly examined for ammunition and other explosives left there by Russian army. This area is larger than England, Wales, and Northern Ireland combined. Due to peculiarities of the terrains and large number of forests in Ukraine, manual demining is necessary in many cases. Kharkiv Eco Park, with the area of 1.4 square kilometers, is the case in point. According to official figures, it takes 5 engineers 90 years of daily works to clear mines. Consequently, it is paramount importance to ensure the productivity and safety of the mine clearance process through the implementation of novel technologies, such as unmanned aerial devices and artificial intelligence. Using them, information about the location of explosive object can be obtained, and then, using GIS and AR, possible routes through the minefield or containment area can be displayed. The roads can be either those that pose minimal risks for the sapper, optimized for complete removal or explosive device, or mixed. This slide presents an overview of current research related to the mining and use of advanced technologies such as unmanned aerial vehicles, artificial intelligence, geographical information system, and augmented reality. Several case studies are discussed. Hierarchical pathfinding A algorithm. This algorithm is applied in geographical information system to optimize paths through areas with varying travel risks. It is particularly prevalent in the mining operations, where terrain poses different levels of danger and accessibility. Parallel genetic algorithm and particle swarm optimization. These algorithms are compared for their effectiveness in real-time path planning for UAVs. The insights are applicable to mine detection scenarios where rapid path adjustment are critical. Augmented reality application. AR has been explored for displaying real-time data to ensure safety in the mine operation, providing operators with visual cues of hazardous zones. While these studies individually contribute to improving the mining, they do not integrate all these technologies into a unified system that ensures both safety and operation efficiency. This research addressed the gap by combining UVs, AI, GIS, and AR into a comprehensive framework for the mining and safe role playing. The aim of research is to develop the system optimized road planning for safe movement through the dangerous area, particularly minefields, by integrated advanced technologies such as UAV, AI, AR, and GIS. The objectives are develop a comprehensive framework for drone-based demining system that integrates AR to provide real-time visual information and enhance pathfinding capabilities to navigate through minefields safely and efficiently. Investigate and identify the tools and technologies necessary for the successful implementation of the drone-based system. Define the challenges associated with pathfinding through minefields and analyze various methods of strategies for overcoming these obstacles. Create and refine the software need to support the drone-based demining system with AR and GIS integration. The high-level architecture, the system that supports safe motion through dangerous spaces includes 3 parts. Control center. This hub manages the UAV flight plans, oversees the visualization of safe paths, and coordinates operational tasks. It ensures the efficient execution of the mining operations by monitoring UAV activity and processing data. UAVs form a group of UAV equipped with sensor collects critical data from the minefield, such as the location of explosive ordnance. This data is then transferred to the data processing center for further analysis. Data processing center, this component processes the raw data received from the UAV swarm, employing advanced algorithm to detect mines and generate safe routes through the dangerous space. It supports real-time adjustment based on challenging conditions in the environment. Existing software can only obtain and display data about mine location. It is necessary to develop and implementing tasks for finding and displaying safety paths and necessary operation connected with. The architecture of implemented software consists of information processing using script writing in C# language, displaying an interactive map implemented using the Mapbox plugin, displaying models of explosive objects for which the AR Core Augmented Reality library is suitable. The tools that provide possibility for implementing this system are described. For creating a system that determines and displays routes on the user's device, it is optimal to use Unity. Unity supports the C# language, which can be used to implement one or more route search algorithm. It is also possible to implement a virtual sharing of a generated map via Unity. The advantage of the software is its multi-platform capability, which allows it to be used on a wide range of devices, including augmented reality glasses. Figure 3 showcases the fields of the UXL and mine probability classes, which are central components of the existing software data structure. The Excel clause includes the following key fields: latitude and latitude, geographic coordinates in the predicted range to simulate the location of exploded ordnance on map, depth, the depth at which the UXO is buried, presented as the value, radius represented the hazard zone of the surrounding UXO. Mine probability class includes the type that defines the category of specific mine or explosive ordnance, and probability. Numerical value represented likelihood of encountering a specific type of mine in the given location. This figure demonstrates how the software models and manage UXO data using this class to store and process information about these means. This data is essential for rendering the 3D models in the augmented reality interface and could be further utilized in the development of pathfinding algorithms to take into account the potential risk posed by each UXO. This slide shows the menu of the developed software. The main menu is shown sequentially, so you can open a window with file processing, a window with mine models, a settings menu when you can change the application language, and a menu for opening the file from local or network storage. The presented screenshots show a glossary of minefield models where you can all see explosive objects presented in the software. A window with a map of the location of mines showing their type, GPS coordinates and other information, and the window displaying the previously specified information in augmented reality. The key elements of pathfinding problems include dangerous spaces, represented a 2D function that defines the area where a pathfinding is required. Set of explosive ordnance SEO. This set don't include information about the location and type of each explosive object within the space. Input and output lines. These lines define the acceptance entry and exit point with the dangerous space. Set of factors. This includes individuals of equipment, each with specific characters that influence their ability to traverse the dangerous space, and time requirement. Specifies the desired time within which the actors need to pass through the dangerous area. The objective of pathfinding problem is to determine an optimal path for each actor or a set of optimal paths for all actors within the dangerous space. The criteria of optimization include maximum safety path, ensuring minimal exposure to explosive threats, or minimum path travel time, reducing the time required to traverse the dangerous space without compromising safety. This slide outlines the mathematical foundation for developing algorithms that can calculate the safest and most efficient roads through the minefields, taking into account the dynamic nature of the hazard. An example of possible pathfinding through the minefield with maximum path safety is shown in Figure 7. An example for possible pathfinding taken by account of different zones of mine dangers is shown in Figure 8. A case when it's not possible to find safety way through minefield and it's necessary to particularly clear mines is shown in Figure 9. The main contribution of the research are following: development of a software architecture, a comprehensive framework integrating UAVs, AI, GIS, and AR to support safe navigation and demining operation in dangerous areas. Software realization, creation of a software solution that displays minefield data and models explosive objects using AR with potential for pathfinding capabilities. Pathfinding problem formulation. Formulated the mathematical problem or safe pathfinding through minefields, optimizing for both safety and efficiency using algorithms of pathfinding. The future research and development activities aim the further advances integration of AI, UAV, AR, and GIS technologies, contributing to safer and more efficient demining operation and ultimately minimizing the risk posed by explosive ordnance in conflict area regions. Thank you for your attention. Please answer the questions.
For your report. And I have a question. Oleg, in your opinion, which algorithms are more suitable for task to pathfinding in dangerous area?
Thank you for your question. I think it's best choice for algorithm will be D star, A star, and X algorithms.
Thank you. And if nobody have a question, we will finish our session, work on our session. Thank you all participants for interesting reports. And I want to invite you connect to our roundtable, which connected with utilization of digital twins and artificial intelligence. And with invite will start at 30 o'clock, and I think all of participants have a list with invited. Thank you, and see you on next conference, DESSERT'. Thank you for your participations.